Good morning, sir. My name is Tirthika. Today's my topic name is Properties of Fourier Series. Types of Fourier Series: Trigonometric Fourier Series, Exponential Fourier Series. Properties of Fourier Series overview. Fourier series decomposes periodic functions into sum of sine and cosine terms. These properties help analyze and simplify complex periodic signals. Understanding these properties is essential in fields like signal processing and communications. In Fourier series mathematics, in a Fourier series decomposes a periodic function or periodic signal into a sum of simple oscillating functions, namely sine and cosine, complex exponentials. The study of Fourier series is a branch of Fourier analysis. Fourier series were introduced by Joseph Fourier 1768 and 1830 for the purpose of solving the heat equation in metal plate. The heat equation is a partial differential equation. Prior to Fourier work, there was no known solution to the heat equation in a general situation, although particular solution where know if the heat source behaved in a simple way. In particular, if heat source was a sine or cos wave. These simple solutions are now sometimes called elegant solutions. In Fourier series does not always converge, and even when it does converge for a specific value of x naught and x, the sum of the series at x naught may differ from the value f x naught of the function. It is one of the main questions in harmonic analysis to decide when Fourier series converge and when the sum is equal to the original function. If function is square in square integrable in the interval minus pi comma pi, then the Fourier series converges to the function at almost every point. In Fourier series, engineering applications generally resumed to converge everywhere except at discontinuities, since the function encountered in engineering are more well behaved than the ones that mathematicians can provide as counter examples to this presumption. In particular, the Fourier series converges absolutely and uniformly to f of x whenever the derivative of f of x, which may not exist everywhere, is square integrable, and it is possible to define Fourier coefficients for more general functions or distribution. In such cases, convergence in norm or weak convergence is usually of interest. In linear property, the Fourier series operator is linear, meaning the Fourier series of sum equals and the sum of the Fourier series. If two functions are added or scaled, their Fourier coefficients combine accordingly. This property simplifies the analysis of complex functions by breaking them into simple parts. Periodicity of Fourier series. The Fourier series of a periodic function inherits the same period as the original function. Changing the period of the function adjusts the frequency components accordingly. This property ensures consistency when analyzing function with different periods. Time shifting property. The time shifting property is a function in time results in a phase shift in its Fourier coefficients. The magnitude spectrum remains unchanged under time shifts. This property is used in signal processing applications when timing adjustments are needed. In frequency shifting property, multiplying a function by complex exponential shifts. It's Fourier spectrum in frequency. And this property in fundamental in modulation techniques used in communications. It allows only translation of signals between different frequency bands. It allows only transition of signal between different frequency bands. And now conjugate symmetry for real function. For real valued function, the Fourier coefficient exhibit conjugate symmetry, and this symmetry implies that the negative frequency components are complex conjugate of the positive ones. If ensures that the reconstructed function remains real valued. And Percival's theorem it relates to the total energy of a function. Total energy of a function to the sum of squares of its Fourier coefficients, and it provides a way to compute the energy distribution across frequency components. And this property is fundamental in signal energy analysis and spectral analysis. And next, convergence properties. Convergence properties. Fourier series typically converge pointwise, or it mean to the original function under certain conditions. In the Dirichlet condition specify when the series converges at point of discontinuity. And understanding convergence is crucial. It's only understanding convergence is crucial for accurate function approximation. Most important in this conjugate symmetry and real function, it is the most Fourier coefficient exhibit conjugate symmetry and ensure reconstruct function remains real valued. Here Percival's theorem diagram we see like formula this theorem type. And convergent properties in understand crucial for accurate function approximation. The waveforms tan x can't be expressed as Fourier series because it has infinite number of discontinuity, and cosecant x can't be expressed as Fourier series because this is also Fourier series infinite number of discontinuity. And differentiation of a Fourier series term by term corresponds to multiplying the coefficients by frequency. Integrating a Fourier series fx is coefficient inversely proportional to the frequency. These properties facilitate the analysis of derivatives and integrals of periodic function. Thank you for giving this opportunity, sir.